So I'm going to talk about work that I've been doing very recently with Nicholas, Sun, and Jiang at NCBI. And the first part through phase one is we submitted a paper to the BioNLP workshop. And then I'll describe some follow work after that. And, right. So the general objective was to investigate deep learning models specifically for information retrieval, with the overall goal being to get towards semantic relevance. And but with the constraints that should be usable in a search engine, so at least the prediction time should be fast. And also wanted to see what can be done without any query expansion or synonym dictionaries, and see how good the promise of deep learning is. So for evaluation, we'll focus on two types of things, robustness, of course, and two kinds of problems that we see in search engines. The underspecified query refers to, most queries are short. Most queries on PubMed are between 2 and 3 words, just like any other search engine, right? So it's not surprising. And I'm talking about text queries, not Boolean expressions. So there are a bunch of expert users who use complex Boolean expressions in PubMed. So we're not counting those at all. Term mismatch talks about query using terms that are different from terms in the document. And the most common example is different spellings. The data that we used were extracted from PubMed's relevance search click logs. On PubMed, the default search order is by time, by recency of publication. And filtered the data to include only simple text queries. As I said, no Boolean expressions. Also, no queries on specific document fields, like you can search for title or author. And then the rest of the filtering basically ensures there's enough data for each query. And relevance labels were assigned by looking at the number of abstract views and the number of click-throughs to the full text, where full text was available.
So you treat both as the same criteria. So you merge the abstract.
Yeah, there was a formula used, and so the relevance numbers are real numbers. The exact formula is not important. There are some relevance numbers. And then the data was split 60-20-20, training, validation, and test. And the training data then had 20,000 queries. And I further balanced the training data so that there were an equal number of positives and negatives for each query. And the reason is that I tested unbalanced, and the balanced one just happened to perform better. And also, the first set of models are classification models, and it's very quick to see whether the model is doing something useful, as different from simply predicting one class when the data is really skewed. So it was partly a convenience thing. So there are two commonly used deep learning architectures in text match or document matching problems. And information retrieval is an example of a text matching problem. The first type of architecture, which I call independent semantic vectors, people also call it Siamese models. A vector is computed from the query and from the document independently, so two different vectors, and then another subnet processes these two vectors to determine relevance. And the second type is local interaction models, where you first develop a pairwise interaction matrix between parts of the query and parts of the document, often words. And then that matrix is further processed by another network. So the main difference between these two is that there's a significant amount of independent processing of the query and document to begin with, and here there isn't. So the attraction of this model is that you can then pre-compute these two components and then use the pre-computed forms in a search engine. So this is the first type of model that I looked at, and looked around literature, and this model from SIG-IR 2015 looked like a nice model, and so I started with that. I will describe each module, but basically there are two scanners. These are convolutional, so again, this was attractive because they're much faster than recurrent networks. And they also combine some lexical match features between query and document, and then classifier subnetwork. So these are the two G's, and this is the F. For word vectors, I used word2vec, ran it on the entire PubMed corpus of around 26 million documents, title and abstracts, and a vocabulary size of around 200,000 words. The query and document scanners in this architecture, as I said, they're single-layer convolutional networks with a filter width of 5, and their hope is to capture at least 5 grams that way, followed by a global max pooling.
Sorry for the obvious question. Can you explain why these are scanners? What's the intuition there?
Oh, scanner is just my word for it.
Okay.
But it's
doing some kind of scanning over the.
So the input is a text sequence of variable length. Variable length in essence, practically it's, and the convolution filter then scans through, and in this case, for each 5 gram, it produces an output and then moves over one step, and for the next 5 gram, it produces an output. And so the output is also variable length in essence, but as I said, in practice, you put a bound.
You put like a bound, like you fill in, you assume that there's a
Pad.
maximum length and your pad is 0.
Yeah.
And then you do have, how many layers do you have?
In their original architecture, just one layer. I'll come back to this, but I truncate the input. So I take the title and the abstract, and I tested different lengths, and 50 seemed to work the best. I'll talk more about that later. And the overlap features are basically traditional lexical features. So that was another thing that was nice about this model, is it combined some lexical features with a deep learning model. And so these are the features that I used in my experiment. These two are taken from the paper, and then I added those 3. And why these 3? Well, I just picked them. The relevance classifier is a 3-layer network, feed-forward network, 2 hidden layers followed by a sigmoid layer, and it predicts a probability. So it's a classifier. Oh, and then I added dropout layers and L2 regularization throughout. So for the evaluation, so start with the traditional lexical models, BM25 and unigram query likelihood. I tested on title, abstract, and title plus abstract, and in this case, the title ones gave the best metrics. And then word movers distance. Are you familiar with word movers distance? Yeah, okay. So this was nice because it leverages the same word vectors, but it's an untrained model. So, and as you can see, it actually does perform slightly better than BM25 and query likelihood.
So can you explain what the word movers is?
Word movers distance? Basically, it's measuring the distance between 2 documents by saying what proportion of each word can be transformed into a word in the document, and the distance between 2 words being the distance between the 2 word vectors, and finds the minimum apportion so that the overall computed distance is the minimum. And the metrics that I'm using are mean average precision and NDCG at rank 20 on the test data. So the first test for the SEV-MOS model, I tuned the hyperparameters, the L2 regularization and dropout levels, And I did some tests for the length of the document input, as I mentioned, and some tests on the number of features. Number of features refers to the number of convolutional filters. And so these seemed to perform the best. And as we can see, the results are not very encouraging. So the question now was, what next?
So what are the baselines? The QLM baseline seems to be
So QLM is query likelihood model, unigram.
in WM.
Word movers distance, and in this case, it's word movers distance on the title and query after removing stop words. And again, I tested various combinations, and that performed the best.
Did you try your model with just the lexical features and not the?
No, that I did not do. Yeah.
Isn't there also, if you're just relying on the title, I mean, that's a major gap. I mean, why wouldn't you use the title and abstract and so on?
In these three, I tested all combinations: title only, abstract only, title and abstract, and these gave the best metrics. These are simply a baseline for me. Here it is title plus abstract, truncated to a certain length, and I tested different lengths. So I'm just showing you the best results I got.
Do you have any intuitions of why this is not working as well as we would like it to? Like the baselines are not like very strong.
Very strong, yeah. That's basically what this slide is about. So the first question was, maybe the model does not have enough capacity, right? So said, okay, add more nonlinearity. And so the obvious place to add more nonlinearity is in the convolutional layer. And instead of using a single layer of width 5, I then used a stack of 3 layers of width 3 each, which get to 7 grams. But there are 3 levels of nonlinearity now. Sample weighting. So I mentioned that each query document pair has a relevance level assigned to it. And so by weighting the samples, I can try to improve the NDCG. The mean average precision is obviously binary notion of relevance, yeah?
Sorry, were you overfitting the training data when you had your first model?
Definitely the metrics on the training data were better. And so the way I tuned was I used NDCG on the validation data.
Okay.
Does that answer your question?
Yeah, it's just that if you were already fitting your training data, then adding more capacity is probably not necessary. But,
Yeah, but it was not just a question of regularization, right? Because I looked for the model that best performed on the validation data.
sure.
I guess to make the question more clear, could you get 100% mean average precision on the training data?
No, and I didn't really look for that. In this case, what I was looking on the training data was accuracy of predicting whether it's relevant or not.
Sure,
And it was not getting to 100%.
Yeah, that's the question. And so, yeah, increasing capacity should help.
You also mentioned your relevance labels were real numbers, but you're training a binary classifier, so you had to pick some threshold.
No, so it was 0, 1. So the relevance levels were 0 for non-relevant, and then degree of relevance beyond that. So it was greater than or equal to 0.
Okay, so they're not fractional relevance labels.
The third intuition was move to a different type of model. So here you can think of the SEVMOS model as charting a region of relevance in some multidimensional real space, right? And this multidimensional real space is in absolute coordinates in which both the query and the document are placed. And so my intuition said that, well, this region will look very different depending on where the query is. And it might be easier for a model to chart a region relative to the query in coordinates that are not, instead of being absolute, are from the frame of reference of the query itself. So that's what led to this approach. So I compute a difference between the query and the document, and then that gets fed into the following subnet. And so this model is what I'll describe next. This then becomes a local interaction type of model. So it's no longer a Siamese or semantic vector model. But again, I wanted to keep it really simple for efficiency. So this is what the delta model looks like. The query and document word vector sequences are fed into a module that computes a difference, and I'll describe what that is. And then it's fed into a scanner, again similar to the previous model. And then the output of the scanner and the lexical features are fed into a classification stage. So the difference features, so instead of computing a pairwise matrix, I instead, for each document word, I find the closest query word and then compute three things: a vector difference, the distance, and the cosine. And so the output of this is the same length as the document. The scanner used a 3-stack convolution with global max pooling, and then again there are dropout layers in L2 regularization. So remember we talked about using a 3-stack convolution instead of a single convolution layer, so that's that. Didn't seem to help in SEVMOS. Then sample weighting, I tried both C1 and C3. C1 actually gave slightly better numbers, but again, not very interesting. With the delta models, things certainly look better. So this is without sample weighting and with sample weighting. So now to drill down into the sub-problems that I mentioned earlier. So I isolated some subsets of the test data. So neg20 plus is a data set which has at least 20 negative or non-relevant documents. Why 20? Because the page size is 20. And the all new word subset consists of queries that contain words not seen during training or validation. And these are the metrics on those two subsets. So in this, so let me just stress the importance of this subproblem, the underspecified query. Definitely at eBay, the most common problem that we used to see was a short query with millions of search results. And so that's what this is targeting. It's not surprising that the lexical models do worse than on this particular subset than overall, right? So remember their original numbers were around 0.35 and somewhere close to 0.6 here. The SEVMOS model and the delta models both actually do better, and delta is showing better results. On the all new words subset, the lexical features perform fairly close to their overall numbers. The SEVMOS and delta models both show a slight improvement.
So I apologize if you already covered this, but how large is the corpus that you're searching over here?
With different queries, there were different number of documents. The way the documents were collected was for every query over a period of time, over a month. So I did not cover this. Every time the query was seen that resulted in a click, the first 20 documents were collected, and then the click document. And so if the query was seen multiple times, this just was accumulated.
I see. And
But what I did then is ensure that I looked at only those queries in this data that had at least 20 documents.
okay, so then when you're evaluating like the NDCG with the neural models, are you evaluating the model?
It's just over that data set.
Okay, and you're evaluating on each document every time you want to like return a result?
With only the documents associated with the query.
With
So
the-
it's a kind of a simulation of a second level ranker you can think of.
which
It's not really as good.
I see. So you wouldn't be able to say like, it seems like you wouldn't be able to embed the documents ahead of time in order to search over the full corpus with this.
Well, that would be the goal. That would be ideal. And with the independent semantic vector approach, you can, right? If you remember, I said you can think of the independent semantic vector model as f of two Gs. And the two Gs, the document Gs can be computed just once and saved. And the query vector can be computed once per search request.
Okay.
Incidentally, just to complete the answer to your question, our real goal is to use this as another factor in a higher level learning to rank model. But in this case, it's convenient to think of it as a second level ranker on its own. So I'm only looking at text and only textual relevance. In PubMed relevance, we look at a whole bunch of other factors like publication, year, and so on.
A question, how do these results compare to the results of the C model? Because you're modifying an existing model, and of course you didn't use the same data set that you had. Is the choice of the data set a major difference, or do you think
Well,
there's also consistency?
the Severin Moschetti model on their original data set performed well. And so it was surprising that it was not performing better than our baselines on our data set.
So none of the points you mentioned as potential reasons for why it's not working seem to have any like it seem to be specific to the domain that you're working on. So why do you think this is the case? Why do you think this is not working as well in this domain?
The problem seems not to be just with this domain. There is a more recent paper from Sigar 2016 in which they compare a bunch of other models and their model, and on some public data sets, Trek and ClueWeb. And if I remember correctly, none of the models performed better than query likelihood. Which is somewhat surprising. The Severin Moschetti model, for example, was tested on data set that looks quite different. There were short pieces of text, and but some of the models that they tested were targeting web search. And so why they did not perform well, I have some ideas about, but not a good understanding. And we can talk more about that in the discussion part.
You think it could be due to a higher proportion of unknown words in your data set?
This is going to be a discussion, so yeah. But maybe you can also define what you mean by unknown, and
Sure.
so let's carry on. As in unseen during training?
Right.
Yeah.
Sorry, I have one more question. So BM25 is not trained, right?
Yes. Well,
The other baselines,
I
are they trained on labels at all, or are they all just
so this is completely non-parametric. BM25 has a couple of parameters, and I tested a bunch and then picked the one that gave the best metrics. Here also I did some testing and picked the one that gave the best results. But it didn't seem to affect the performance much. So a lot less testing here. An example. So the query is cryoglobulinemia. I actually don't know what this is. But, so these are the top 3 relevance levels, and as ranked by the delta weighted model, and in this case, it also picks up on an alternative spelling. And then what you see in BM25 and word movers distance is they seem to prefer shorter titles. And remember, these two are actually targeting just the title, whereas this is targeting title plus some words in the abstract.
How do you embed words you haven't seen before? Do you just use a single unknown vector, or
I'm sorry?
how do you embed words that you haven't seen before for training that are out of vocabulary?
So all the word vectors are pre-trained using word2vex in an unsupervised manner. And then there's no further tuning of the word vectors during the training of the model.
But at test time, if you encounter, or do you never encounter words you
Oh,
have vectors for?
so then the only thing remaining is words that fell below the minimum frequency threshold. And for those words, I assign a random vector of small values. And they're all get the same one vector.
In this example, how would you expect, based on just title and abstract, to be able to figure out what the right answer is? I mean, I wouldn't be able to do it. Like, I see that word, cryoglobulinemia, but based on all these titles and abstracts, they all feature the word. So what makes you think there's even information in the title and abstract to be able to do this?
So that's an interesting question. How would I expect a model in general to answer these questions, right?
Well, I'm asking, like, based on just the information you're giving the model, is there enough information there? It feels like you need information about more meta information about, which ones are like which are seminal, these kinds of things, and that's actually more important to a query like this than actually the text.
And that is probably what limits performance of these models.
Some sort of error analysis there?
No. So that's something that I have not looked at. However, what I would expect this to do is at least to do an even-handed coverage of related topics rather than focusing on a single topic. And so how do you determine, what are related topics? Well, hopefully the word vectors are giving you that. The pre-training of the word vectors.
And so you expect that, like a word like cryoglobulinemia would have a word vector representation that's robust because it appears a lot in these kinds of things. Do you use character level representations?
No.
So you can't take advantage of the fact that a lot of these things are potentially more than just determinism, like some of their parts, like the morphology of these things.
Correct.
Especially in these domains.
Yeah. So, I mean, basically, this is a small step towards the long-term goal, right? And that long-term goal is quite a much more interesting and more complex goal. Here's another example where things don't work so well. And in this case, the most relevant document from the labels is psychological risk factors in headache. And clearly, psychological risk factors, you need some level of semantic understanding that this relates to depression. And yeah.
What are the numbers before the titles?
So yeah, as you guessed, these are the titles of the documents and these are the relevance levels.
On a scale of, like, what does relevance level
Yeah, I did not show you the formula that they're all greater than 0. Higher means more clicks on the document to the abstract, and also possibly more clicks on the full text.
And what's the scale of it? Is it
They go up to around 100 or so.
But you said your training treated all positive numbers the same?
Yes,
Positive versus zero.
in this case.
Labels doesn't, the training doesn't care the difference between 6 and 3.
Yeah, only NDCG cares.
Your metric, but the training.
Correct. Not in this case. So WMD and the delta weighted model are correctly picking up on migraine as being related to headache, but that's as far as it goes. So there's a whole bunch of semantic knowledge to be learned that this model is not doing. So now move on to phase 2. And so instead of classification models, now I looked at pairwise ranking. And pairwise ranking, the training data is now a triple of query in 2 documents, where document 1 is more relevant than document 2. And the loss for one sample is basically you're saying that make the score for document 1 be at least the margin, in this case 1, greater than the score for document 2. So from the same data, I now extract triples, and so that resulted in about 7 million triples. And then I experimented with sample weighting, no weights, and then weights using these 2 formula. The output stage now needs to change because we're not predicting a probability, we're simply predicting a relevance score. And so you don't want the output stage to be limited in the range, like a sigmoid is, and for that matter, even a hyperbolic tan. And so what I didn't mention is that in the previous models, except for the final output stage, which was sigmoid, all the other activation functions were rectified linear unit. So I tested rectified linear unit as the final output stage, and it is less limited, but it still only produces positive numbers or non-negative numbers. Found that models would often fail to converge. So moved to leaky rectified linear unit, and then that worked. And the leaky rectified linear unit is not limited in its range at all. And so I used the leaky ReLU in all the stages, not just the final output stage. For training, used eta delta with early stopping, and as I mentioned, the hyperparameter tuning was done using validation data NDCG. And so let's look at SevMouse again. So in black are the original numbers, and then the blue are the pairwise models. And so the numbers here, so this is the original model simply converted to pairwise. Here I added BM25 on title as a lexical feature. And then here, this is a weighted version of the original model. Weighted version of this model, and this is a weighted version of this model. And you can see that basically things don't look interesting until here, which is adding BM25 as a lexical feature and weighting. The delta model, here things are more interesting again. The pairwise model is performing better than the corresponding classifier model with only 32 convolutional features in this case instead of 256. And definitely adding BM25 helps. Log damping versus square root damping of the relevance levels don't seem to make much difference. Quick test of different number of features. So even a delta pairwise model with BM25 with only 16 features outperforms the classifier model. Moving to 32 makes things slightly better. Moving to 64, it's about the same. The difference in number of parameters is huge. So again, the overall goal was efficiency. So more parameters makes it less efficient. So now the question is, which lexical features work the best? So tested a model with 32 convolutional features and no lexical features at all. And this is the inverse of somebody asked whether I tested lexical features only, but I tested one with no lexical features. So even that outperforms the classifier model with lexical features. And legacy lex is using the same lexical features as were used in the classifier model. And then I did a greedy search over a space of a bunch of lexical features and then picked the top 3, and these are the results. And that gives the best performance. I show validation because really this is the column that I'm using to pick the best model. Yeah.
So did you, and you might have mentioned this earlier, but why did you try a regression model against the relevance score instead of doing like a classification or the pairwise thing?
Well, this is in a sense a regression model.
Well, I mean, I'm thinking about your example from earlier where the one that was ranked highest was not chosen, but maybe you would have a higher chance of ranking that one the highest if you treated it as a regression problem. So things like that would, the model would be incentivized to score it higher.
So possibly direct regression may perform better than classification, but pairwise ranking generally tends to perform even better. The further advantage being that in pairwise ranking, the relevance levels don't need to mean the same thing across queries.
Oh, I see. So there wasn't a consistent.
In this case, I don't trust the relevance levels that much. And in general, it is hard to assign relevance levels to different queries and actually mean the same thing. And pairwise ranking in general does give you better performance partly because it does not make that assumption. So to conclude, the main difference between the SEVMOS and the delta approaches is one is an Siamese or independent semantic vector approach, has the benefits of allowing you to pre-compute document and query vectors. In the delta approach, you can't. However, it's performing better, in other words, better metrics, and a much simpler model in a lot fewer number of parameters.
Is it the case that the SEVMOS model has much faster runtime? Because you can pre-compute all the.
Yeah, with the pre-computation, yes.
So do you have like approximately numbers for how much is this one faster than the other?
No. I did compute some numbers a while ago, and what I have not done is I computed numbers for the delta model for the classification model with 256 features. Not for these, which are much smaller. And this is where things really start getting interesting.
Do you think it's fast enough, either of them, to be integrated in a production system?
Not the 256 features, no. No, I would not. From my eBay trained sensibilities, I would not. So next steps. So as I think I did mention, right? I'm throwing away all sentence structure. It's just a sequence of words. So the obvious next thing to do is to look at sentence structure and build a vector for each sentence. And then you can try, so hopefully the following will work. I can pre-compute vectors for each sentence and then do the delta approach of query word against sentence vector. Also wanted to try a more sophisticated convolutional level. So there's a recent work from Facebook called gated linear unit that you may know about, which makes it easier. Easier is not the right word. Anyway, you get better results by stacking these. And then this is what I'm actually in the middle of right now, is looking at some track data, just so I can get a comparison with other models. That's it. Thank you. Now we can do the discussion.